Hello, it's December 12th, 2021, and I'm Ken Eklund, and I'd like to play this video and then stop it and give you my view of what's happening.
So uh, uh, light has this speed. All these waves travel at the same speed. It doesn't matter how fast you're traveling, they will always travel at that speed. So that gave rise to the theory of relativity. So I'm going to show a little movie which illustrates this. Imagine I have a little, let me go back a little bit and start it again. So I'm going to have a little trolley with a laser in the middle, which is going to emit pulses of light in two directions. We're going to look at the trolley, first of all, standing with it, or traveling with it. It's traveling down some road, and we're going to be traveling alongside it and watch those light rays going. That'll be a pretty obvious picture.
Okay, I have to stop it right there just so you note what he said. He said that's a pretty obvious picture. That's where, see, he skipped over explaining. He skipped over explaining or proving if his assumption that the light that we're going to see what he's telling us we're going to see. And I don't think we're going to see what he just assumed that we're going to see. And he said that's a pretty easy picture. I'll go on.
Then we'll say, no, imagine I stand on the side of the road and the trolley goes past. What do I see? The classical picture is that the light emitted forward is going to be going faster, and the light emitted backward is going to be going slower than the speed of light. Okay, so that's what we'll see in this first movie. This is made by an engineer at IBM, this movie, called Udi Aharoni. So here we are. We're plotting.
Okay, I'm going to stop it here because what he assumed was that uh, when this. Okay, let me start. If first, this is a very strange trolley. They're calling this a trolley, and it's moving in this direction towards me. So, and then this is a laser gun. Let's say it shoots out a photon, and it hits this whatever this is supposed to be. He didn't say. Let's just call it a sensor. So he shoots a photon at this sensor. Now it'll hit the sensor if the trolley's not moving. Okay, but once you get this trolley moving at half the speed of light or something, what's going to happen is the photon, when you shoot the photon out, it won't hit this anymore because this is gone. This has moved forward. So the photon will just keep going straight, and it'll miss the sensor and just miss the whole trolley and continue on in a straight line. So this is what it would look like. It would, every time you shoot photons out, they go in a straight line, and the trolley is moving forward away from them. See, and but he wants us to believe that if you got this trolley moving at half the speed of light, and you shoot a photon at this sensor, it's still going to hit this sensor. Now, why would that be? Because when you shoot the photon out, the photon's not connected to the trolley. It's not part of the trolley. It's just floating in space. So it might have some forward inertia, but inertia tapers off quickly. So, and that's, I can prove that if you want, but um, but what would happen would it has a greater force, has a great force in this direction. So it would be shot out of the, and it would just go straight. You see, it would be going straight. And then the cart at half the speed of light, it's moving out of the way. It's going to move forward. The photon is just going to keep going on. So you're going to have a bunch of straight lines like this. You're not going to have these lines. In order to have these lines, the what do they call it? The laser, the photon gun. Uh, the laser would have to anticipate where the cart is going to be. So let's say the cart is here, and it's going to shoot a photon out, uh, and you would have to predict that the sensor is going to be here, and you'd have to point the gun ahead of the cart, and then shoot the photon, and then the cart and the sensor catches up with it, and then it hits. For that to happen, this doesn't happen. What they're saying here just doesn't happen. Um, it's and they base relativity on this. It's really something.
Another dimension. This is time. This is time going upwards. Let me show you that one again. So the cart is moving along the road, but we're going to plot this with time going perpendicular just so that we can see the history of what happened. So time is going along here. Every time the laser emits these two pulses, they travel outwards. And you see they're going exactly at the speed of light because they go 1 unit along and 1 unit down. Okay?
Now, what he's going to say here is, if you look at it from this angle, uh, it looks like this photon traveled farther than this photon. But light is, but they have another assumption, which isn't really correct, that light always travels at the same speed. So um, it would take longer for this photon to get from here to here. Therefore, something has to give, and it's time that gives. So it's the perspective. It's how you're looking at this, and time is changing all around. Like depending on on where you're standing
now,
and viewing
I
it.
was standing on the road watching the trolley go past, this pulse would be going much faster. Let's imagine the trolley is going at the speed of light, or nearly the speed of light. This pulse is going at twice the speed of light. This pulse is going hardly going at all because it's going, the trolley sending it backwards, but the trolley itself is moving very fast forwards. So that's what the classical picture of the light trajectories would look like. And
Well, I can stop it here. I mean, he goes on to talk about Einstein. See, Einstein really gets into the time warping.
So any notion of simultaneity is gone because they were simultaneous if I was traveling with the trolley, but now I'm moving relative to the trolley, they're not simultaneous anymore. So lengths change, times change, and
Yeah. So now what he's saying is um, that if you're standing over here, you might see the light hit this sensor before it hits this one. Uh, you know, just a lot of very, very strange stuff. It's like the same photon is not even hitting the center, this sensor. Now they're saying it is hitting the sensor there and on this side too, but at different times. Give me a break. Give me a break.
uh, simultaneity is gone. So here's the picture, the correct physical picture that the light wave took a very short time for the back of to hit the back of the trolley, takes a very long time to hit the front of the trolley. The spacing between these pulses is longer. This is time dilation. So if you want to stay young, you travel a lot. Okay, because then the time between the beats of your heart will be much longer. Okay.
See, I don't believe that. I think our body has to keep a chemical reaction going at a certain pace. We need oxygen and nutrients to keep our machine going. And if we slow that down, uh, we will die. We will die. We're not going to slow down in time and still live. And this guy's very jolly. He's got some funny things to say, but I think these physicists should take it more seriously because they're telling us that this stuff is real, and he looks more like a magician standing up there. I played in bands for a lot of magicians, and it's a show, it's diversions, it's presumptions, and you know and then you got to then you're it's wonderment, like how did that happen, how does this happen, how does time slow down, or it's wonderment. And then but the later you figure out, oh, he did, oh, it's a trick, he did it that way. Okay, I didn't know that. So but my journey has been very interesting since a friend of mine said that he worked on GPS, and I've been watching a lot of videos since then, and there's this one guy I really like. He's great. He's great. His name is Distintis. Distinti. 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 And it's Robert Distinti, and he's made a lot of videos. He calls it Distinti's Universe, and they're all very good. It's very, it's a lot more practical. It's like a real practical view of the universe. And so I'm getting closer to understanding GPS. I've found out that uh, it might not be as mystical and as like Einstein. It might be like just more down to earth. There's this thing called, I'll get into it in another video, but um, there are things called clock bias that I want to study, and it's been around a long time, and it explains why clocks can slow down and speed up. But anyway, it's a great day outside. I'm going outside. Thanks a lot. Bye.